Hello students, in this video we'll use Chebyshev polynomials to find the smallest L-infinity norm of a monic polynomial. So let's consider a monic polynomial p of x, which is just going to be x to the n plus a n minus 1 x to the n minus 1 plus a n minus 2 x to the n minus 2 all the way down to a0, like that, okay? And it's monic because the leading coefficient is equal to 1 over there. So it's a monic polynomial degree n. And I'm going to consider x on the interval -1 to 1. And so here's the theorem of Chebyshev. It states that the L-infinity norm of this p, which is just going to be the maximum over the interval -1 to 1 of the absolute value of p of x, like that, is bigger than or equal to 2 to the 1 minus n, which is the L-infinity norm of 2 to the -n minus 1 Tn of x, and where Tn, of course, is the nth Chebyshev polynomial. So here, Tn is going to be cosine of n cosine inverse of x. That's the nth Chebyshev polynomial. Okay? And now we need a fact about this nth Chebyshev polynomial. So we know that the lead coefficient of this thing, so of course we know that t, for example, t0 of x is equal to 1. We know that t1 of x is equal to x, like that. And then let's look at t2 of x, for example. So t2 is going to be the cosine of this thing over here. And so we know that t2 of x is going to be x squared. So it's going to be cosine of 2 cosine inverse of x, like that, okay? But the cosine is really going to be 2 cosine squared of the argument. So that's cosine inverse of x minus 1. And so I just have a 2x squared minus 1, right? And so if we look over here, the degree of this, that's a 0 order degree. The lead coefficient has what exponent over here? The exponent of the lead coefficient is 2. That corresponds to 2. So it's always 1 less than 2 to the power n, right? So in other words, the lead coefficient of Tn is 2 to the n minus 1. And we can prove that by induction, okay? All right, excellent. So we're going to use that fact over here. And what we want to do is we're going to prove this by contradiction. So here goes the proof by contradiction. Suppose that's the maximum -1 to 1 of absolute value p of x was strictly less than 2 to the 1 minus n, which we know to be exactly this thing over here. And what we'll do now is we're going to define a new polynomial. I'm going to define Tn tilde to be 2 to the n minus 2 to the 1 minus n times Tn, right? If we define Tn tilde like that, what can we say? Well, if the lead coefficient of Tn of x is 2 to the n minus 1, then this thing is a monic polynomial. Then Tn tilde of x is a monic polynomial of degree n. Okay, that's going to be an important observation in our proof, okay? So, okay, that's great. And so now let's make some observations about these Chebyshev polynomials. So I need a lemma in sort of in the middle of our proof over here to sort of make some observations. It's a simple lemma to prove, right? And so what do we know about the roots of Tn? So the roots of Tn are, so let's look at the roots. So what will the roots be? The roots are going to be of the form cosine of 2k minus 1 over 2n pi for k being equal to, starting at 1, because we'll get a 2 pi, 2 all the way up to n, like that, okay? And that's easy to see because if I plug in cosine to inverse cosine over here, I'm going to have n times this thing. If the cosines go away, so I'll have n, we'll cancel out with that n, and I'll have a 2k minus 1 pi, right? So we're doing about the cosine, for example, when I plug in k equals 1, I'm going to have a 2 minus 1, that's a 1 over 2, so that's pi over 2. The cosine of pi over 2 is equal to 0. When I plug in n equals 2, I'm going to get a 3. Cosine of 3 pi over 2 is equal to 0. So the cosine of all the odd multiples of pi over 2 up to 2n minus 1 over 2, and that will give us exactly the last time that the Chebyshev polynomial will vanish. So I have n, exactly n roots of my Chebyshev polynomial. And so now what can we say? Well, we can say about the extreme values of the polynomial. The extreme values of the polynomial occur where? Well, it's actually going to occur at both endpoints too. We can check that easily. Are of the form cosine of what? Cosine of just k pi over n, where k goes from 0, 1, 2, up to n, okay? And I'm including the endpoints in there as well. So how do we check that? What's the derivative of cosine? The derivative of cosine is negative sine, and we have some square root, which is not going to vanish anywhere except at the endpoints, right? So I have to plug in the endpoints. And what values are going to annihilate sine? Well, we have to plug in cosine to eliminate the inverse cosine, and then I'll have n that will eliminate that, and then I'm going to have the sine of a multiple of pi. And the sine of a multiple of pi is 0, so that proves these are extreme points. And what can we say about the cosine of these points? So I'm going to call these points over here. So let's call these points. So these are my cosine points, and these are the values over here. Let's call these values over here. Let's call those zeta k, okay? So what is Tn of zeta k? Tn of zeta k is going to be, well, let's plug it in. I'd have cosine of n times the inverse cosine. We'll cancel that out. Then I'll have a k pi over n. And of course, that's just the cosine of k pi, which is negative 1 to the power k, okay? Excellent. Now, what can we say? So now here's the observation to make. Of course, I have 0 up to n of those things, so I have the endpoints as well. And so now let's consider, and now what would Tn tilde be? Well, Tn tilde of these things, so Tn tilde of zeta k is just going to be basically just 2 to the 1 minus n, right, times negative 1 to the power k, like that, okay? Good. And so now let me define let's call this r of x, which is going to be what? Which is going to be the difference of these two things, Tn tilde n of x minus p of x. Okay. And now what can I say about this polynomial over here? This polynomial is going to change signs, and let's explain why. So the first observation about this polynomial is this thing, the degree of r. Well, they're both monic polynomials of degree n, so this p starts with an x to the n, and so does this Tn tilde. So the x to the n cancels in both of them. So it's a polynomial of degree n minus 1. So this is a polynomial of degree n minus 1. Or less, right? It's less than or equal to that, right? But the worst it can be is n minus 1, okay? Good. And now what can I say? I know that if I plug in any of these minimum points, what happens if I plug in, for example, this zeta 0, for example? If I plug in zeta 0, well, this expression over here is going to be positive because I know that I'm assuming that this L infinity norm of this polynomial is strictly less than that. So when I plug in, for example, r of zeta 0, I'm going to have a what? I'm going to have a 2 to the power 2 to the n minus 1, right? Minus p of zeta 0, right? But no matter how large p of zeta 0 can be, it can never be as large as 1 minus 2 to the n minus 1. So that number over here is positive, right? If I look at r of zeta 1, that's going to be what? That's going to be a negative 2 to negative 1 over n, and then minus zeta 0, right? P of zeta 0, zeta 1 rather. And that thing over there is going to be negative because there's no way that can sort of catch up to the negative 2 to the minus zeta 1. So in other words, between zeta 0 and zeta 1, there's a root of r, right? So r has roots on zeta 0 to zeta 1, zeta 1 to zeta 2, all the way down to what? All the way down to zeta n minus, do I have this in the backwards order? No, these things are going to be ascending, so we have to sort of change the order of these things. So let's change the order of those so that they're going up over here. So let's make sure we have this correct, right? So let's see. So which of these is smaller over here? So the zeta 0 is the cosine of 0, which is 1. So that's going to be the biggest over there, right? So we have to go in descending order, right? So I go from zeta n to zeta n minus 1, because these things are decreasing, right? All the way down to zeta 1 to zeta 0, like that. So I just have to flip the order because they're in descending order, because I'm doing cosine of k pi over n. And now let's count over there. So how I have one interval over here down to n intervals over here. So this function r has roots on n intervals between -1 and 1, right? So in other words, r has n roots that are distinct. Okay? But r is a polynomial of degree at most n minus 1. So we can have at most n minus 1 roots. And I just proved that r has n distinct roots, and that's a contradiction. So we've contradicted the assumption that the maximum of this thing over here was strictly less than 1 minus 2 to the n. So in other words, the maximum of this thing has to be at least 2 to the 1 minus n in overall size. So we've used these Chebyshev polynomials to show that if you want to construct a polynomial where there's equally spaced roots to sort of minimize the absolute largest that a polynomial can be in a certain interval, the Chebyshev polynomials give you the the way that the roots of that polynomial must be distributed in order to minimize the overall L infinity number of a polynomial. Thank you very much.